Sequences. Last time we looked at arithmetic and geometric sequences. Let's take a look at an example sequence. Maybe an is equal to -1 raised to the n times n over n plus 1. Writing out the very first few terms, we can think about n equal 1, n equal 2, n equal 3, and maybe n equal 4. So when n is equal to 1, then -1 to the 1 is negative. Then you'd have 1 over 1 plus 1, which is 2. So you'd have -1/2. When n is equal to 2, and also when n is equal to 4, this term is going to be positive. And likewise, when n is odd, this term will be negative. So that makes it easy. We jump from negative to positive to negative to positive. And then we can just concentrate on filling in n over n plus 1. For n equal 2, 2 goes on the top, and then 3 goes on the bottom. We jump back and forth between negative and positive, so the next term would be negative. We take a look at what our value of n is. It's now 3, so the numerator is 3, and then increment that by 1 to get the denominator. And repeat. So now we're at a positive term, 4, over increment that to 5, and so forth. So first term, second term, third term, fourth term, and so forth. Good. Another example might be taking the general term an to be 1 over 2 to the n. Then the first term has n equaling 1, so that's 1 over 2. The next term would have n equaling 2, and you just think, well, what is 2 raised to the 2? That's 2 squared, or 4. The next term would be 1 over 2 to the 3, and that's 8. We can pause here and take a look that what we're doing is we're starting somewhere. And to get to the next term, what we're doing is we're taking the previous term and we're multiplying it by 1/2. Take the current term to produce the next term is to multiply by 1/2. So 1/8 has a successive term of 1/16, which has a successive term of 1/32, 1/64, and so forth. Note that this is a geometric sequence. And our beginning value is 1, and our common ratio is 1/2. Good. Oh, excuse me. Our beginning value is 1/2. Excuse me. And the common ratio is 1/2. Excellent. All right. So what we want to do is now think about limits. So looking at these values, starting at -1/2, then 2/3, then -3/4, and then 4/5. And we can see that if we were to let n go out to infinity, let's actually do that. Let's do limit n goes to infinity of an, and then we can plug in what our definition of an is, -1 to the n times n over n plus 1. So this guy here is going to ping pong between plus and minus, but this quotient since we're taking n out to infinity, we can divide both top and bottom by n. In the numerator, we'd get n divided by n. In the denominator, n divided by n plus 1 over n. And we can look at this piece here and take the limit as n goes to infinity, and that would give us 1 over 1 plus 0. So this piece here is going to 1. However, this piece here is always swapping back and forth between plus and minus. And we can see that this limit does not exist. On the other hand, on this geometric sequence example of 1 over 2 raised to the n, we can see by inspection that terms get smaller and smaller and smaller. We can also notice that all of these terms are positive, yet they're all getting smaller. And we also know that this can be written out as 2 to the negative n. And if we think of exponential functions, this is essentially an exponential function with base 2. And because the exponent is a negative, it'd be a decay exponential. And it would limit to 0. The only tricky part is that we're only evaluating this function at counting numbers. If we draw a nice little graph to highlight that idea that we just went through, might have something like xy coordinate plane, decay exponential, y equals 2 to the negative x. Let that be f of x. We know that this tends to 0 as x goes to infinity. And then in terms of the sequence, we can come along and we can pick off the counting number inputs. And what we would be doing in taking a limit as n goes to infinity of a sub n, where a sub n is 2 to the negative n, is simply watching the y-coordinates of these blue dots. But since they're following the graph of this exponential decay function, they're going to tend to 0. Good.